Dear students, after studying this module, you shall be able to understand the basic concept of organic solids, classification of organic solids, organic molecules acting as conductors, organic molecules exhibiting superconductivity, the basic concept of polymeric conductors and superconductors. The organic solids are the compounds with carbon atom as their essential structural elements and in broad sense include all solid state materials like organic molecules or polymers. Under the umbrella term of organic solids, a wide variety of natural solids such as wood, cotton, industrial products like plastics and rubbers are covered. The organic solids with the parental properties are insulators, but with the development of technology, the functionalized organic solids became an active components in the electronic or photonic devices. The functionalities of these materials are mainly based on their capability to carry and transport charges and neutral excitations. In present context, the organic solid refer to those organic materials that show conducting properties in the form of crystals, thin films or glassy state. The inorganic solids as inorganic semiconductors such as silicon or germanium have dominated the electronic market since the beginning. The organic solids like organic semiconductors have emerged recently as a new class of electronic materials and have become strong competitor of inorganic semiconductors in different electronic industries. The organic solids possess high processability, mechanical flexibility and low cost as their main disadvantages. The first study of the conductivity on organic solids was done on polycyclic aromatic compounds such as anthracene crystals as a prototype of organic semiconductors. This was done by forming a semiconducting charge transfer complex salts with halogens. Later, during the 1970s, the conjugated polymers established themselves in the field of organic semiconductors. The area of conducting polymers became so important that for the discovery and development of conductive polymers, A.J. Heger, A.J. McDiarmid and H. Shirakawa were awarded the Nobel Prize in Chemistry 2000 jointly. The technological developments have helped the organic solids in their applications as electronic devices. One of the earliest application was done by Tang and Van Slyke in 1987 when they fabricated thin film organic light emitted diode OLED by using a pi conjugated molecular material from tris 8-hydroxyquinolinato aluminum as shown in figure. Tris 8-hydroxyquinolinato aluminum is a coordination compound. This is a complex of aluminum 3 cation and the anion of 8-hydroxyquinoline. The aluminum atom is coordinated with nitrogen and the oxygen atom of hydroxyquinoline. Another polymer based OLED was developed by Friend and his group at Cavendish Laboratory in Cambridge. They have used a conjugated polymer poly-p-phenylene as shown in figure. The other application of organic semiconductors include their use in organic solar cells, chemical sensors, organic lasers, etc. The organic solids with their properties are further termed as organic conductors and organic superconductors. They usually possess a conjugated pi electron system in a skeletal structure. There is still a long way to go for physicists, chemists and engineers to work together before the large-scale production of organic electronic devices become possible. Classification of organic solids. On the basis of intermolecular interactions, organic solids can be classified into two types: nonpolar organic solids and the polar organic solids. In the nonpolar organic solids, van der Waals interactions are present. These forces are weak in comparison to the covalent bonding. In the polar organic solids, both ionic bonding and the van der Waals forces exist. In these type of molecules, the positive and the negative charges are separated and located on different molecules. The ionic bonding present in these molecules is weaker than that in the inorganic solids. On the basis of the molecular weight, the organic solids can be classified into two types: conjugated small molecules. These are low molecular weight organic solids which possess conjugated pi electron system. These molecules are usually crystallized into ordered arrangement by sublimation or evaporation. They are deposited from the gas phase by using the method of sublimation or evaporation. Conjugated polymers. These are high molecular weight organic solids which have molecular weight in the range of polymer and possess conjugated pi electron system. These molecules can only be processed from solution. They are deposited by spin coating or printing techniques. The molecular structures of various organic solids are shown here in the given figure: perylene, fluorine, anthracene, ruberine, pentacene, tetrathiofulvarine, fullerene, phthalocyanine, polythiophene, polyaniline, porphyrins, porphyrazine are some of the molecular structures of organic solids. The polyaromatic hydrocarbons like anthracene, ruberine, pentacene, fluorine, etc. have been shown to be good candidate for the construction of electronic devices. These compounds are made up of fused aromatic rings. They are potential candidate for the electronic devices due to their high charge mobilities in the crystallized films. The polyaromatic hydrocarbons are also used extensively in OLEDs as emissive dopants or charge transporting materials. The organic solids having conjugation systems with the heteroatoms like sulfur and nitrogen are also used as organic semiconductors. The heteroatoms are present either outside or inside of the aromatic rings. For example, in polyaniline and polyphenylene sulfide, the heteroatoms are present outside the ring and hence are the example of the outside case. In the polymers like polythiophene and polypyrrole, the heteroatoms are present inside the ring and hence are the example of inside case. Some metal complexes of macrocyclic heteroaromatic compounds like tetrapyrrole, including phthalocyanins, porphyrins and porphyrazines, have also been applied in organic electronics and photonics. Organic conductors. Conductors are certain materials that conduct electric current. The process is called conductivity. The organic molecules involved in conduction are called as organic conductors. They range from semiconductors to conductors. An important breakthrough was achieved in 1960 by Kepler et al. Through the addition of an electron to TCNQ, as shown in figure, forming a salt. Later, another work was done on TTF, TCNQ, where conductivity reached to about 8000 ohms centimeter inverse at about 59 Kelvin, but below this conductivity reached to very low value. The organic compounds conduct electricity when either extra electron or electrons are present or vacancy of the electron exists. For an organic conductor, there must be small energy gap between the valence band and the conduction band derived from the HOMO and the LUMO of the organic molecules. HOMO of the electron donor species and LUMO of the electron acceptor species, that is the highest occupied molecular orbit and the lowest unoccupied molecular orbital of the species must be appropriately placed in the charge transfer complexes. The characteristic features of the donor and the acceptor are: for the donor, the molecule must possess low ionization potential, they must have electron donor group attached, they must possess maximum polarization property. For the characteristic of an acceptor, the molecule must possess a high electron affinity, they must have small energy of LUMO, which is lowest unoccupied molecular orbital, they must have electron withdrawing group attached. Organic superconductors. Superconductors are certain materials that conduct electric current with practically zero or no resistance. The process is called superconductivity. In present group of superconductors, materials require low temperature for functioning as superconductors. An organic molecule possessing the properties of a superconductivity is known as organic superconductor. Also, organic molecules are hope for the design and synthesis of high temperature superconductors. The first major step was accomplished by Wood et al. In 1970 with the synthesis of tetra-thiafulvalene TTF. This molecule has fulvalene skeleton with 4 sulfur heteroatoms and can easily donate electrons to the electron accepting species. Its derivative BEDT TTF acts as a donor molecule for a molecule organic superconductors of charge transfer type with the acceptor molecules such as C60, piscine, M-dimit 1,3-dithiol 2-thiooxo-4,5-dithiolato, which is shown in figures. The organic superconductors are classified into two groups: charge transfer type superconductors and single component superconductors under high pressure. Single component superconductors. The single component superconductors are divided into 4 groups: closed shell organic solids under high pressure, organic neutral pi radicals, beta-ionic zwitterionic radicals of TCNQ and TTF derivatives, and lastly transition metal complexes of phthalocyanine and TTF dithiolates, charge transfer type organic superconductors. The charge transfer organic superconductors require a donor and an acceptor atom for its functioning. The molecule TMTSF, which is shown in figure, with heavy atom substitution provided 8 quasi one-dimensional superconductors. The possible combinations were TMTSF2X, where X is PF6, arsenic fluoride, antimony fluoride, NBF6, TAF6, ClO4, ReO4 and FSO3 with Tc less than 3 Kelvin. Another molecule that is used in superconduction is bis-ethylene dithiotetrathiafulvalene, BEDT, TTF or ET. These molecules form planes which are separated by anions. The ET molecules on interaction with same anion can form a variety of charge transfer complexes having different packing. These types of complexes show polymorphism, that is, have the same composition with different crystal structures. They also exist in different compositions based on crystal growth conditions. Polymeric conductors and superconductors. The high critical temperature superconductors are explored on a polymer system containing both conduction path and highly polarizable pendants. This helps in the formation of Cooper pair in the conduction path using electron-exciton coupling. The studies have been done on two inorganic polymer superconductors such as polysulfur nitride and black phosphorus existing in the crystalline forms. In case of polysulfur nitride, there is a partial electron transfer from sulfur to nitrogen, leading to the development of an ionic character. The weak interaction between the chains of SN polymer gives quasi one-dimensional structure. The superconductivity observed at the critical temperature of 0.26 Kelvin. The Tc increased under the pressure less than or equal to 3 Kelvin. In the case of black phosphorus, there is a two-dimensional layer structure. The superconductivity observed under pressure with critical temperature at 6 Kelvin and pressure of 16 GPa. These polymers showed superconductivity without doping. The polyaniline is most widely studied and used polymer as conductor. The others include polythiophene, polyisothionaphthalene, polypyrols, and polyphenylene vinylenes. Some polymers on doping exhibit conduction. The doped polyacetylene exhibited conductivity which is higher than that of any previously known polymer in the range of 10 to the power 5 Siemens per meter. One of the main property of the conductive polymer is conjugation. In conjugation, the alternate single and double bond exists between the carbon backbones of the polymer. However, conjugation is not only the required condition to make the polymer material conductive. Hence, doping is done to make them conductive and more efficient. The dopant helps in charge carriers through extra electrons or holes. The dopant atom or molecules are either strong oxidizing or reducing agents. When any polymer is doped, there is a creation of either positive or a negative charge carriers and hence acts as acceptor or donor. As shown in figure, a polymer can be doped by the method like self-doping, gaseous doping, ion exchange doping, solution doping, radiation-induced doping, and an electrochemical doping. To summarize, the organic solids are the compounds with carbon atoms as their essential structural elements and include all solid state materials like organic molecules or polymers. The organic solids with the advanced electrical properties are termed as organic conductors and organic superconductors. The organic solids like organic semiconductors have emerged recently as a new class of electronic materials and have become a strong competitor of inorganic semiconductors in different electronic industries. The area of conducting polymers became so important that for the discovery and development of conductive polymers, A.J. Heeger, A.J. McDiarmid and H. Shirakawa were awarded the Nobel Prize in Chemistry in the year 2000 jointly. The technological developments have helped the organic solids in their applications in the electronic devices like fabricated thin film organic light emitting diode OLED by using a pi conjugated molecular material. The other applications of the organic semiconductors include the use in organic solar cells, chemical sensors, organic lasers, etc. On the basis of intermolecular interactions, organic solids can be classified into nonpolar and polar organic solids. on the basis of the molecular weight. The organic solids can be classified into conjugated small molecules and the conjugated polymers. Superconductors are the materials that conduct electric current with practically zero or no resistance. The process is called superconductivity. In present group of superconductors, materials require low temperature for functioning as superconductors. An organic molecule possessing the properties of a superconductivity is known as organic superconductor. The first major step was accomplished by Wood et al. In 1970 with the synthesis of tetrathiophulvalene and octaxanes.